Hi everyone. So in this video, I will talk about the accelerometer. Since we already covered also the LDO before, so I'm not going to go in details on it. Just one thing, so you can see I add the LCSC part number, so I know where to buy it from. And another thing you haven't learned, so here I add the specification. So you can see this plus 3.3. If I click on it, then it will highlight, Altium will highlight all my 3.3 connection here. So to skip this, right click and then clear filter. So how to add this? So simply, if I remove it from here, if you write add, then it will show you different different connection here, and then I just put 3.3. And in this way, when I press here, it will highlight all the 3.3 lines for me. So it's just an option. So let's start with this accelerometer here. So all this connection is based on the data sheet. So first we have the VDD pin is the main supply for this sensor. And then we have pin 3 IO VDD is the supply for the input-output interface. So in our case, it's the I2C lines. So here we have SC. So even I don't have even to go to the data sheet because I wrote it here. So chip select count. So for I2C, so if I put this selection bin, I put it high, I connect it to IOVDD, then I can use my I2C communication protocol here. And also that's because this accelerometer exactly you can use it in two ways. You can use it in SPI communication or I2C communication. So if you want to use the I2C protocol, then you have to connect this to IOVDD. So we can see that from the data sheet. So here is our pin. So active low for SPI communication and connect to IOVDD for I2C communication. And you should not leave it floating. So that's what I did. Also for the power supply, you have always to refer to the electrical section, which is somewhere here. Yeah. So this is the supply voltage for IO VDD and VDD. So the minimum is 1.7, typical is 2.5, and the max is 3.6. And we have here 3.3, so we are safe to run this accelerometer. And for those two decoupling capacitors, I choose 100 NF. This is also a recommendation from the datasheet. So you can see here for the VDT, they said we should use 100 nanofarad ceramic capacitor, and also for the IO VDD, also they recommend to use 100 nanofarad ceramic capacitor. So that's the reason I have those two here. Then I have this ADDR, so the address bin. So this bin is to select an address for our sensor here, and that's make the microcontroller will be able to talk to this sensor. So in our case, we put it to ground, and that's what I wrote here. So it will have the address of 0x1e if it's grounded, and if we put it to the VCC, it will have another address. So if you program any accelerometer before or any I2C protocol, that number you defined it in the code, then the microcontroller can talk with the sensor. So the benefit, we can configure two addresses. So if I have a same sensor, another one of this sensor, then I want to catch the reading from each one individually. Then I can put one to the ground and another one, the address I will put it to the VCC. And in this case, our microcontroller can talk to both individually. So where I got this from is also from the datasheet, which show you when you ground this pin ADDR, it will give you this address, and when you put it as a VCC, then it will give you this address. And here also they put you, if you have different sensors, how you can connect all this sensor together. And don't forget, there's always a pull-up resistor, which I also included. So my pull-up resistor, I just put it here. So 4.7 kilo ohm. I should remove this. And where I got this value from, if we go to the datasheet again, so they said on the note for I2C communication, the minimum pull-up resistors is 1.5 kilo ohm on the SCL and SDA pins. So then I used 4.7 kilo ohm as a pull-up resistors. So now we cover all those pins on the left side. So then I have this trig pin. So I already wrote briefly what it does. So in this accelerometer, it's a buffer which has 512 byte temporary storage area. So instead of the microcontroller having to read every single measurement, then this sensor will collect all this measurement inside its buffer, and then it will send all the measurement to the microcontroller. So in my case, I don't want really to use this feature, and this FIFO is stand to first in, first out. So any data this sensor will measure, so first data will go first out to the microcontroller. Second data this sensor will measure will go to the microcontroller in this sequence. So in my case, I don't want this trig pin to be used, and that's what they said. If you don't want it to be used, then connect it to the ground. So if you really wanted to use it, you can connect it to the one of the GPIO of the microcontroller. In case you have an application, you want to collect different data and store it inside the buffer of your sensor. And after a while, you want to fetch all this data together in one row. Then you can use this trig bin. So the last thing is the interrupt bin. Of course, you can read about this trig also in the datasheet. So they also write some explanation of it, and they wrote further information in the datasheet. So the interrupt bin, so basically I can use it to wake up my microcontroller. Let's say if I have a fall detection application, then my microcontroller can go to sleep mode, and then I can wake up my microcontroller using this pin, and that's why I wrote MCU INT, so it means it's going to the microcontroller. Also, this SDA and SCL, I always write MCU, so I know it goes to the microcontroller. So when the fall detection detected, then this pin will send a signal to the microcontroller in this pin, and that will wake up the microcontroller from the deep sleep. And also remember to put the LCSC part number so we can use it on the bill of material. So that's all about our accelerometer. Thanks.